welcome back to this tutorial on connectedness. So what do we have now? We want to show that connectedness is actually preserved under homeomorphisms. So we are claiming that connectedness is a topological property. Now a topological property is the one which is preserved under homeomorphisms. What does that mean? As in, if you have a homeomorphism, from x to y, and suppose that x is connected. If you make an assumption that x is connected, since f is a homeomorphism, then that should imply that if x is connected, that should imply that y is connected, as long as f is a homeomorphism. So connectedness is a topological property, i.e., that is, it's preserved under homeomorphism. So what are we going to do? So we are going to show this this way. We are going to let x and y be topological spaces. F from x to y be a homeomorphism. Now suppose that this thing is how can I call it? It's something which is two-sided. You can suppose that x is connected and prove that y is connected. And in the previous video, I think we have showed that. I don't want to prove that. We have proved that the image of a connected space, and a continuous map is connected. Image of a connected space and a continuous map is connected. Because a homeomorphism, by the way, a homeomorphism is a continuous map, bijective, and also the inverse is also continuous. That is a homeomorphism. So you can suppose that x is connected, then prove that y is connected. Now in the previous video, we supposed that x is connected, then we prove that y is connected, as long as f is continuous. So we can as well suppose that x is connected. We can as well use that similar argument to show that y is connected. Yeah, since a homeomorphism is a continuous function. So what are we going to do? So in this case, I'm going to suppose that y is connected, prove that x is connected. So suppose that y is connected. F is a homeo, implying that f inverse is continuous. F inverse is the one. Suppose that y is connected, f a homeo, f inverse is continuous. This should imply that we want to show that x is connected. F inverse, observe that f inverse is the one which takes y to x. Maybe I can fix it here. This f inverse, it maps y to x. It maps y to x. So we want to show that x is connected. We're going to prove this by contradiction. By way of contradiction, suppose that x is not connected. This implies that there exists open sets A and B in X, open sets A and B in X, A and B being non-empty, disjoint such that what? Such that X is equal to A union B. A union B. A and B form a separation of X. What do we have? We have that, observe that this map here, this map, F inverse, taking Y, this is Y, and now this is X. This is Y, this is X. F inverse is a continuous map. We want to show that X is connected. We have supposed that X is not connected. There is a separation of X. We have open sets here. This is A and this is B. They are separating X. They are separating X, and since this is a continuous map, the pre-image F inverse is a continuous map. Since F is a homeomorphism, so the inverse function is a continuous map, implying that the pre-image of this, the pre-image, this forward map is F inverse. So the pre-image of A is now F inverse A, which is equal to F of A. F of A. So the pre-image of A, which is F of A, is an open set in Y. Also the pre-image of B, which is F of B, is an open set in Y. Where are they open set? Since F inverse is continuous map. So we can proceed. So observe that F of A and F of B are open. They are open sets in Y. Moreover, F of A intersection F of B. Now this is equal to F A intersection B. I'm trying to take F outside because, by the way, this thing is not always true. This is not always true. It's only true if at all the map is one-to-one and injective. One-to-one, which is the same as saying that the map is injective. A homeomorphism is a bijection map, so it's one-to-one. It's actually injective. So I can do this. So in this case, this is fine. However, it's not always true. It's not always true because of that reason. It only works when the map is continuous. When the map is injective. Sorry. It only works when the map is injective, and for a homeomorphism, the map is injective. So A intersection B is an empty set, so this is equal to F of empty set, which is an empty set. So you realize that the open sets, this one and this one, they are disjoint. Let us try to compute the union. A union F of A, F of B. So I can write this as F of A union B. Why am I taking F outside? F is a homeomorphism. A homeomorphism is an injective map. You can do this as long as the map is injective. So this is equal to F of A union B. A union B is X, and F of X is Y. So you realize that F of A and F of B form a separation. They form a separation of y. They form a separation of y. This is a contradiction to the fact that y is connected. This is a contradiction. The fact that we suppose that y is connected. So this is a contradiction implying that our original assumption was wrong. So this implies that x is connected. X is connected. So connectedness is a topological property which is preserved under homeomorphisms.